Imagine that we were a group of curious 18th century mathematicians interested in polyhedra. At some point of our investigation, we would like to study some global properties of polyhedra, namely, the properties that are invariant under a large class of deformations. Some natural global properties we might consider are the number of vertices, edges, and faces. We can stretch and bend edges and faces so that the lengths, angles, areas, and volumes change, but we can never change how many vertices, edges, and faces there are by stretching and bending without tearing the surface apart. You may see where I'm getting at. In the spirit of curiosity, we plotted the number of vertices, edges, and faces of some familiar polyhedra on a table, and we tried to find some interesting relations. After playing around with the data, we noticed a surprisingly consistent relation. V-E+F is 2. We ask ourselves, is it true that this relation holds for all polyhedra? Motivated by this question, we put forward the following conjecture. For all polyhedra, V-E+F is 2. This is a rather strong conjecture. Given any polyhedra, we obtain the relationship between V, E, and F, so if we know two of them, we can derive the third. Our intuition told us that this is a conjecture more than worthy to tackle, so we immediately set out to find a proof. Here's one that we may come up with. The proof consists of a thought experiment. Imagine the polyhedron as a surface made of thin rubber. Cut out and remove one of the faces, and we can stretch and bend the remaining surface onto a flat board without tearing the surface. Although this process alters the length of edges and the areas of the faces, it never changes the value of V, E, or F other than decreasing F by 1, nor the incidence relationship among them. For example, it is clear that if a vertex is contained in some edges, it is still contained in the very same edges after the deformation, so we are left to prove that V-E+F is equal to 1 in this map that consists of a bunch of polygons. The next step is to triangulate this map. In other words, we can repeatedly connect two vertices with an edge such that a polygon is split into two. In the end, we'll get a map consisting of only triangles. At each step during this process, we add an edge to split the face into two. In other words, E increases by 1, while F increases by 1. Therefore, triangulation does not change the value of V-E+F. Notice that it is generally true that if we remove one of the triangles, say this one, then V-E+F is unchanged. In this case, V doesn't change, E decreases by 1, and F decreases by 1. If we are always able to remove triangles in this way, then we can reduce the map to a single triangle. When there is only one triangle, V-E+F is 1. Remember that we have removed the face in the beginning to spread the remaining surface on the flatboard. So for the original polyhedron, V-E+F is equal to 2 as claimed. So all that is left for this proof is to verify that there is a sequence of removing triangles that keep V-E+F unchanged until only one triangle is left. Let's call an edge hanging if it is not connected to any other polygons. If a triangle has one hanging edge, then removing this triangle will always decrease E by 1 and F by 1. If a triangle has two hanging edges, then removing this triangle will always decrease V by 1, E by 2, and F by 1. Removing a triangle with three hanging edges will cause V to decrease by 2, E by 3, and F by 1. In all these cases, V-E+F doesn't change. At each stage of this process, there is always a triangle that has at least one hanging edge. Therefore, if we remove triangles of this kind one by one, we will be left with a single triangle for which V-E+F is 1. So, we have proven the Euler polyhedron formula. What's even better, the thought experiment explains why this formula is not a mathematical coincidence. We can see, roughly speaking, that a map constructed by removing a face from a polyhedron always satisfies V-E+F equals 1. So by transforming the map back to the three-dimensional space and adding a face to enclose the region, we get back the polyhedron, for which V-E+F is 2. The truth value of this conjecture is settled once and for all, and the conjecture becomes a beautiful theorem. Back to the 19th century. Imagine that one day after we published the result, we received a note. The note contains a polyhedron consisting of a cube with a cavity. For this polyhedron, you can count it yourself, V-E+F is 4. The mathematician sending the note claims that this is a counterexample to the conjecture. We, however, were baffled by this claim because we thought that apparently this is not a polyhedron at all. A polyhedron is not just a set of polygons. The polygons must form one and only one surface, and any point on the surface can travel to any other point on the surface without leaving the surface. But this cube with a cavity has to be bounded by two surfaces, so it is not a polyhedron. Feeling assured, we clarified our definition of a polyhedron to the mathematician. A couple of days later, we received another note. This time it described a pair of tetrahedra sharing an edge. We counted the number again. V-E+F is 3. Unlike the previous example, this polyhedron meets our first definition. It only has one surface. Another pathological case, we say to ourselves, our definition of polyhedra still isn't clear enough. Apparently, there are two polyhedra in this structure, not one, and so of course V-E+F is not equal to 2. How can we make this rigorous? In a normal polyhedron, only two faces meet at an edge. But for this polyhedron, the edge shared by the two tetrahedra is contained in 4 faces. It is not hard to imagine that each time an edge connects more than 2 faces, a sort of unwanted multiple structures is generated. So we replied to the mathematician with our new definition. A polyhedron is a set of polygonal faces bound by precisely one surface such that each edge is contained in precisely 2 faces. But after a couple of days, another note arrived, this time describing a pair of cubes, one sitting on top of the other, and the part where the 2 cubes touched was drilled open. For this polyhedron, V-E+F is equal to 3. I wouldn't go on here since the tale is long enough for us to see the point. Call our method of dealing with counterexamples the method of monster barring. As shown, monster barring is untenable because if all the counterexamples are monsters, there are a lot of them, perhaps an infinite number of families of them. We barred these monsters from ruining our conjectures by clarifying the definitions of the objects in the conjecture, but these definitions get longer and longer, and we won't even know if our chain of definitions will terminate. What if there are so many kinds of monsters that all definitions consist of a finite number of words cannot exclude all of them? If counterexamples cannot be excluded by clarifying definitions, we shall acknowledge that there is a certain validity with these counterexamples. And we shouldn't call these examples monsters, but just exceptions. We shall acknowledge that the set of polyhedra is large and very complicated, and that only a certain subset of polyhedra satisfies V-E+F is equal to 2. What is the domain of validity then? Notice that normal polyhedra that we imagine are usually convex polyhedra. Maybe the domain of validity of the formula is just the set of convex polyhedra.
Now, the improved conjecture might be correct. We might actually give a proof of it. Even so, this approach of guessing the domain of validity before proving the conjecture, the approach that we'll call the method of exception barring, is also problematic.
Wouldn't it be bad if this improved conjecture misses many non-coincidental instances of polyhedra that satisfy the relation? More importantly, what's the problem with the original proof that makes a narrow domain of validity necessary? Here's a method that brings our original proof back to the picture. The proof doesn't actually prove what we set out to prove, but rather it decomposes the naive conjecture into several sub-conjectures, or we shall say lemmas. A careful proof analysis shows that our proof uses the following list of lemmas. First, any polyhedron after having a face removed, can be spread out onto a plane without tearing apart any part of the surface. Call the figure on the plane obtained in this way a map. Second, any map can be completely triangulated by adding diagonals. After each addition of a diagonal, E increases by 1 and F increases by 1. Third, there is a sequence of triangles in any triangulated map such that the removal of each triangle results in one of the following. E decreases by 1, F decreases by 1, E decreases by 2, V by 1, and F by 1. E decreases by 3, V by 2, and F by 1. And we are left with one triangle after the full removal process. If we apply our proof to the counterexamples, we'll see that at least one of the lemmas is refuted by the counterexamples. For example, in the case of a cube with a cavity, the cube, after cutting out a face, cannot be spread onto a plane. Call a polyhedron simple if it can be spread onto a plane after having a face removed. We can modify the conjecture so that the simplicity of the polyhedron is set as a condition. For all simple polyhedra, V-E+F is 2. Then we can proceed on our list of counterexamples and see if any other lemmas are refuted. It is clear that the example of the twin tetrahedra is not simple, so it doesn't refute our improved conjecture. However, the counterexample of two cubes, one sitting on top of the other, is simple. We can indeed take out the face at the bottom and spread the polyhedron onto the plane. But when we proceed with our proof and perform the triangulation, we'll notice that the ring-shaped face in the middle cannot be triangulated. If we draw a diagonal, any diagonal, it simply adds an edge, but not a face. So the second lemma is false, but we can reframe the second conjecture and add it as a condition of our improved conjecture. What we need for the second lemma to be true is that in each face, any diagonal inside the face splits the face into two. A face that satisfies this property is defined to be simply connected. Hence, the improved conjecture goes like this. For all simple polyhedra, each face of which is simply connected, V-E+F is equal to 2. At this point we may ask, shall we perform this process again and incorporate the third lemma into the condition as well? It turns out that the first lemma actually implies the third, a result that is proved much later in the 20th century. For our purpose, let's assume we can supply a proof. Since all the false assumptions are made into the conditions, and since the deduction from the assumptions is valid, the improved conjecture becomes a theorem. Let's call this method lemma incorporation. Compared to the method of monster barring or exception barring, this method has the advantage of effectively utilizing a false proof. Although the proof doesn't prove what it sets out to prove, we can treat it as a proof of a different conjecture, one that incorporates the lemmas into the conditions. Because of this, we can reasonably improve the naive conjecture without leading to much unnecessary reduction in the content. But the method of lemma incorporation wasn't as widely used in the 19th century as it is today. Monster barring and exception barring still form the first instincts of many working mathematicians. For example, John Queer, in a paper that aims to defend Euler's polyhedron formula, writes vehemently in regard to the cube with a cavity, that a polyhedron, at least from the classical point of view, deserves the name only if, before all else, a point can move continuously over its entire surface. Here, this is not the case. This first exception of Lullier can therefore be discarded. Many other counterexamples are dealt with in the same way. It is a common pattern in mathematics that a proof of a conjecture generates a concept, opening up a field of inquiry. In the example, the proof of Euler's polyhedron formula gives rise to the concept of simple polyhedra and simply connected faces. Both end up becoming important concepts in modern-day topology. However, monster barring and exception barring would, in some cases, hinder the emergence of proof-generated concepts. To further illustrate proof-generated concepts and their relationship with monster barring and exception barring, we'll give a historical example.
The primitive conjecture is this. Any convergent series of continuous function is continuous. Cauchy gave a proof to this conjecture using his epsilon delta definition of continuity and convergence. The proof was widely regarded as rigorous, so the primitive conjecture was put into use without hesitation. However, the situation was more complicated than he thought. Somewhat strangely, a counterexample was discovered by Fourier. Consider the following convergent series. This is an alternating sum of some cosine functions. Apparently, each term of the series is a continuous function, but what is the limit function? Let's try to visualize this limit by computing the partial sum, and see how the partial sum changes when m gets progressively larger. As m approaches infinity, we can see that the partial sum becomes separate horizontal lines joined by vertical lines. In an intuitive idea of continuity, a function is continuous if we can draw its graph without lifting the pencil from the paper. This is how Fourier sees it, so in the beginning, he didn't consider this as a counterexample to the primitive conjecture at all. However, using Cauchy's own definition, it can be proved that this function is discontinuous at the point of the jumps. So this example comes into direct conflict with the primitive conjecture under Cauchy's framework of analysis. The presence of a counterexample is threatening to make a fatal blemish in Cauchy's rigorously constructed analysis theory. How can we resolve this? Abel, a prominent French mathematician known for his proof of the insolubility of quintic equation, stepped in. His first reaction to the counterexamples was to start guessing the domain of validity. He considered that the study of mathematical analysis usually deals with power series, and so he proposed an improved conjecture. This improved conjecture is equivalent to the claim that the convergent series of continuous functions in the form of a power series is continuous. This statement, while correct, is by no means exhaustive. What's worse, it didn't even point out the problem with Cauchy's original proof of the conjecture, so restricting the domain of validity through guessing, or in our terms, exception barring, wasn't addressing the conflict at all. It was not until 26 years later until German mathematician Seidel resolved the contradiction. I'll put Cauchy's original proof on the screen, and I encourage you to pause and walk it through yourself. The problem that Seidel discovered was that in order to make the last steps, we need an assumption that there is an m greater than all n epsilon z, where z is a real number. This condition, the hidden lemma, is equivalent to uniform convergence on R in modern formulation. By incorporating this lemma into the conjecture, we have reached an improved conjecture. The uniformly convergent series of continuous function is continuous. The proof of the improved conjecture is correct, so the conjecture becomes a theorem, and subsequently, the study of uniformly convergent series leads to many other beautiful results. Uniform convergence is a perfect example of a proof-generated concept. It only takes shape after a careful analysis of the original proof. Using lemma incorporation, proof-generated concepts come naturally in the process of incorporating the lemmas into the set of conditions. On the other hand, exception barring is not as effective in generating fruitful concepts because we usually have to use the concepts we already know, such as the power series, to guess a domain of validity. But remember, it took 26 years just for mathematicians to spot the small mistake and add one more clause in the condition to address the crisis. One has to ask,
Why does it take so long? One answer to this question has something to do with the tradition set by Euclid that theorems precede proofs. According to this tradition, one must get the theorem right before one proves it. If the theorem turns out to be false, the proof ideas are discarded because there is no point in trying to prove what is false. Under this mindset, the only options for mathematicians to deal with counterexamples were either to argue that the examples are not real counterexamples after all, or to throw away the proof, take a guess at its correct domain of validity, and prove the improved conjecture. This also explains why lemma incorporation, a method that seems so intuitive and effective from a modern standpoint, didn't arise naturally in the place of monster barring and exception barring. The content in this video is largely based on Imre Lakato's book, Proofs and Refutations. Although this video is already quite lengthy, I've left out many things in the book that I would like to share. For example, the discussion of Euler's polyhedron formula doesn't end here. Among the polyhedra that I put on paper, there is a counterexample to our lemma-incorporated improved conjecture. I challenge you to find that counterexample and figure out why exactly it refutes our improved conjecture. The book proceeds to illustrate some philosophical and mathematical difficulties of the method of lemma incorporation, along with many other topics that are historically significant and still relevant to our current mathematical research. I highly recommend Lakato's book to all learners of mathematics who wish to delve into the subjects more deeply. Some math students might want to ask, why does it matter now? Monster barring, exception barring, lemma incorporation, and all that. After all, we just want to learn some mathematics, and we haven't touched on any research yet. What can we get out of these discussions beyond simply hearing some interesting stories? Lakatos writes in his book that many textbooks are written in an authoritarian way. A typical authoritarian textbook proceeds like this. We are first presented with some definitions that we have no clue what's going on. We are told, just accept them and get familiar with them. They will make sense to you eventually. Some propositions follow, and they are proved with clever and elegant argument. Eventually, the propositions lead to a significant theorem. We'll find that all the proofs are correct, and they connect beautifully to prove the theorem. But we wonder how mathematicians could possibly devise these clever definitions and prove ideas. We proceed anyways, thinking that, in the end, our mathematical intuition will grow mature enough so that we can come up with them by ourselves in research. However, the development of mathematical concepts doesn't work this way. We've seen, by our examples of Euler polyhedron's formula and uniform convergence, that struggles and challenges characterize the beginning stage of the development of a mathematical theory. These mathematical theories are subject to criticism, most notably by counterexamples, and mathematicians have to re-examine proofs and come up with refined definitions and improved conjectures to address these criticisms. In the authoritarian textbooks, however, we are only presented with the elegant, polished body of infallible truth, but not the long way of proofs and refutations that mathematicians have gone through. Lakatos, therefore, suggests a reformation of textbooks and teaching. He advocates for the heuristic approach, one that emphasizes the context in which concepts and theorems are produced, as opposed to the deductive approach. I generally agree with Lakatos. From the standpoint of math learners, however, it is not easy to find high-quality, non-authoritarian textbooks and other resources. Nevertheless, I believe that the historical significance of proofs and refutations that Lakatos has illustrated sheds light on an effective way of reading the more authoritarian textbooks. The following method of textbook reading is what I call the static method. Read the definition, get familiar with it, and read the propositions, theorems, and their proofs. Make sure to understand each step of the proof. Use the exercises to familiarize with the concepts and theorems. Throughout the whole process, keep in mind that things will make sense eventually. I believe that we shouldn't learn math like this. We could read textbooks in a more enjoyable way, which also leads to a better understanding of the materials. I call this the dynamic method. The biggest difference between the two is that with the static method, we treat mathematical concepts as fixed objects, while with the dynamic method, we emphasize the formation of these concepts and we try to simulate this process through our own questioning. The method proceeds as follows. When reading propositions, play around with them. Prepare a list of representative examples, including the classical ones and the more quote-unquote pathological ones, and study how they fit into the propositions. See what happens to the proof when a hypothesis is removed. Study the converse. Then use the information to imagine the starting stage of the field of study. For example, ask ourselves, can this hypothesis be a refuted lemma that is incorporated into the condition of a more naive conjectures? Is the proposition important because of an obvious converse? Is it a generalization based on some examples? At some point in these investigations, we can come back to the definitions and trace how some of their parts are necessary for the development of the theory. These interpretations don't have to be historically accurate. After all, they are just heuristics. But in this way, we are able to deconstruct the arguments in the textbook and trace it back to its naive ancestor, recreate the struggling process of mathematical discovery, and therefore place ourselves in a framework in which things make more sense. For instance, consider this theorem. If f sub n is integrable for each n, and f sub n converges uniformly to fx, then the limits of the integral f sub nx is equal to the integral of the limits of f sub nx. We may ask, can some entries in the sequence f sub nx be not integrable? Well, no, because then the right side of the equality will be undefined. What happens if f sub n does not converge uniformly? Since this is a more sensible question, we can feed some examples and look at the proof. By looking at the examples, we may find some sequences that do not converge uniformly and do not satisfy the equality. By studying the proof, we may figure out where specifically the proof uses uniform convergence as a condition. With these, we can treat uniform convergence as the lemma incorporated into the condition of a more naive conjecture, one that does not have the uniform convergence condition. We can also close the textbook sometimes and take small exploratory excursions ourselves. We can ask, can I generalize a certain theorem to other domains? Can I make an abstraction based on several proofs that use the same ideas? In the above example, we can keep exploring by asking questions like, is the lemma corresponding to the uniform convergence condition general enough? We can also find simple examples, such as x to the power of n, in the closed interval between 0 and 1, which is not a uniformly convergent sequence, but the equality above still holds. The example is so simple that it leads us to think that uniform convergence is a rather strong condition, and there must be a more general criterion. The investigation of these questions, along with some research, may lead us to Arzel's dominated convergence theorem, a significant result in measure theory. Take another example. Suppose we learn the fundamental theorem of algebra, a theorem stating that every polynomial with complex coefficients has a complex root. We may ask, what about polynomials with integer coefficients, real coefficients, coefficients in the ring of Gaussian integers? If the polynomials cannot be written as a product of linear factors, what are the irreducible polynomials besides the linear ones? If we also learn the proof of the theorem, we can start by analyzing the proof. After all, one of the biggest lessons that Lakatos has taught us is to never ignore the proof. One of the proofs of the fundamental theorem uses Liouville's theorem, which claims that every bounded entire function is constant. What happens if only the derivative is bounded? Is it possible to classify those entire functions? We should keep in mind that during this process, however, that these questions don't always lead to new results. Some questions may be trivial, and some questions may be way too hard for us to answer.
However, we can still understand the theorems better by asking these questions, trying to answer them and doing some research. because this process engages us to rediscover mathematics in a quasi-historical framework. It would make a highly rewarding learning experience even if we only prove a rather insignificant result. So, let's ask questions and rediscover.